And we can start. Okay. It works?
Yes.
Nice. Okay. So today we continue with working with the strings, but firstly, and nearly 80% of today's lesson will be about deterministic finite automaton. So, first part of today's lesson about definition and properties of this model. So, deterministic finite automaton. What is it? It's in the first view, it is graph. It is directed graph with some states as the vertices. And we know that we have initial state of our automaton, and we have the final states that we mark with the double circles. So it's equal to graph with vertices equal to states of the phi. We have one vertex that is distinguished from others and names as initial vertex, initial state. Have some vertices as here that we can mark with the double circles, and we say that it is the final states of our automaton. And we have, of course, edges in this graph. And edges, it is the most important part of this graph, because if we define edges different from that that I now say, we can find different automatas, and for example, we talk about non-deterministic finite automaton. but not now. I think we talk about it in 15 minutes. So, what about edges? Firstly, it is a directed graph. So we write here some edges as the arrows, as usual, for the directed graphs. But each edge has a symbol from the alphabet. Yes, we know that alphabet, it is set of some symbols. And we set for all of these edges the character that the character that will be connected with this edge. So the fourth property of this graph that each edge why we want to talk about this unique class of the graphs and why we say that it is deterministic. It is the fifth property, the fifth part of the definition, that if I see, for example, I try to find all the edges that start with the vertex S, I see that the characters on it are different. If for all edges we can say that the characters are different on the arrows or on the edges that start with this vertex. So in this case we say that the automaton is deterministic. Yeah. If I draw it as the next slide. It is deterministic. If for all vertices characters associated with this characters that are associated with the edges that start with the vertex V, the characters are different. So, firstly, why we need to talk about Dufay? Because Dufay is connected with the regular expressions. Do you know what is the regular languages? Okay. So,
Yeah, also the
yeah. Okay. In some tasks, we can face with the languages. What is it? For example, if we set the alphabet A, we can say that the sequence of the characters from this alphabet, it is the word. Yeah. Say that. This alphabet. It is a word with n characters. And then we say that A in power n, it is words that have the length equal to n, and A with the asterisk, it names as or clean star. So it is equal to the union of all the words. And we say that the subset of this set, it is language. So, in some tasks we can face with the languages, that is subsets of A with a star, that is set of some words. And of course we can classify languages by its structure. And in this case, you can face with the regular languages, with the, for example, context-free languages. Uh, And now, do you hear me? Oh, okay. Yes. So, do you remember what is the path in the directed graph? Do you remember what is the path in the directed graph? Yeah. So, okay. About paths and div A. Example that if we have, for example, this if we have this div A, and for example, this vertex 1, 2, 3, 4. So, we name this automaton with the character A, and we say that RA it is language of this automaton. It is equal to words, and we can see at the words as at the passes in this graph. For example, I can connect with the word ABA path that start with the vertex V with index 1 and ends with the vertex V with index 4. So, if we see that it is initial state and it is final state, if using these characters, we can start with the initial state and end with the final state, then we say that this word will be in the language of this automaton. And if we start with the, for example, if we try to find path from initial state by this word, you see that it ends with the vertex V2. So it isn't the final state. So we say that this word not in the language LA. So in the common case, it says that language contains the words such that if we start and find the way from the initial vertex to the other vertex, this vertex that is the final vertex in the path will be in the final in the set of the final states. Yeah. As here we say that the set of this vertex, it is the set of final states. So as we can see in this example, if we have automaton, we can find some language that is connected with this automaton. But it is true that this connection works in the both directions. So for all of the languages, we can find the automaton. But it is necessary to understand that the languages must be from the class that names as the class of regular languages. And this connection will be between regular languages and deterministic finite automaton. So, what is the regular languages? It is languages that has inductive definition. We say that all finite languages will be in the class of the regular languages. Yeah, such that the number of the elements is less than the infinity. So it is the first part of the definition of regular languages. Then we say that if we have two languages, sorry guys, we try to repair the signal from the video camera. Там сейчас показываются настройки камеры.
По себе режим лайфа получается. Но он работает.
Ну, первый раз сталкиваюсь с таким. Нет. Фотография. Работает. Okay. It works. So, if we have two languages from the class of the regular languages, then we say that the union the intersection or difference is two in the regular languages. And you know what is the concatenation of the words? It says that if we have two words then concatenation of these words equal to the sequence that starts with the word U, and then it continues with the words we. Yeah, concatenation of the words. So if we have two regular languages, then we say that the concatenation as the concatenation of the words from first language and from the second is 2 in the regular. Yeah, and you can see that if we write second property and the third, it is equal that all finite languages in the are contained in this class, because we have no ability to construct infinite language by the union or intersection or concatenation, but there is the unique operation that can make infinite language. So if we have L in the class of the regular languages, then we say that L with the star, that names as the Kleene star, it is equal to omega in the power of n, where n equal to 0, 1, or other natural number, other integer number, and omega, it is the word from the language L. So must be in the regular language. So by the induction we say that all of the languages that we can construct as a concatenation of the finite languages, or concatenation of the languages that we can construct by the Kleene star, or etc. By induction we say that all of the languages that we can make, it is the regular languages. It is the regular languages. So, for example, for all regular languages, we can write regular expressions. Example, I can say that L1 equal to this regular expression. What does it mean? It means that, for example, here when we write the word, it is the language with one word. Then this part of the expression, it is equal to language that we can construct it by the Kleene star of this language. Then we can concatenate this language with the words A. Yeah, it is equal to and it is concatenation these two languages. And if we write this vertical line, we mean that it is union of these two languages. So all of these words, it is a language L with index 1. And I make next example why regular languages are connected with the deterministic finite automaton. For example, I can draw the same automaton as in the previous example. It was equal to, oh no, A, B, A, B, and it was the final state is the start state. So, if we try to imagine how we can start with this vertex and end with this vertex, we understand that all the words that start with this vertex and end with this vertex, their structure equal to prefix with the characters A, B, A. It is the unique path from the Q0 to Q4 without the cycles in it. But there are a lot of passes from Q0 to Q4 that have circles in it. Yeah, because we can go from this from Q0 to Q1, then Q with index 2, then go to Q with index 4, and then go through these circles a lot of times. So we can repeat this part a lot of time. So it is equal that omega in the language that can express by this regular expression. So this automaton has this language. And it is a regular language, of course. So if we have deterministic finite Altman, so we have some language. And of course, it is true in the other direction that if we have regular language, then we find DFA A such that L A, it is the language of this automaton, is equal to L. So, try to solve some tasks that are connected with the div A. For example, input data, it is the sequence of the numbers that are equal to 0 or 1. And for example, we can say that the number in the binary system that is equal to this number is A. And we need to find R such that A R equal to 0, 1, or 2, and A minus R is divided by the okay, and do you remember, did you face with this task before? No. Okay, and The difficulty of this task that n can be very large. Now, so if it is equal to, for example, 10 or 20, you can parse it as an integer, store it, and find the residual of it. But if it is equal, for example, for 1 billion, you cannot store it because it is very large number, and if you try to store it, you understand that you need to use big data, and it is very complicated. So you try to find the way to solve it and not use more than all from one space. We want to find the algorithm to solve it with the without a lot of memory. So we can say that if we read some characters, maybe it will be equal to b, and this word will be equal to c. And, for example, if we know the solution of the task B, can we find the solution of the C? We know that number that has these characters in the binary realization, it is number that equal to twice b plus 1, plus a and plus 1. Do you believe in it? Do you believe that c equal to twice b plus a with index m plus 1 plus 1? And do you hear me? The question is that if we can represent B as the in the binary system as a sequence A from A1 to AM, and we can represent C as the sequence of A1 from A1 to A with index m plus 1, then we can say that C equal to twice B plus the last character. And all of these characters is equal to 0 or 1. So do you understand why it is true? No, okay. So I can write here an example. For example, if in the binary system we have such number, what is it? What is it? What is this number? It is equal to 1 plus 4 plus 8 plus 16. Yeah, because we can write this number as the sum of 1 multiplied by 2 in the power of 0 plus 0 plus 1. And it is equal to 29. Yeah, 29. Okay. And then we can see in this part it is and what is this number? Yeah, it is 14. And you can see that this number 29 is equal to twice 14 plus 1, because if we represent 14 as the sum of the pairwise multiplication of these numbers and 2 in some degrees, you see that it is equal to yeah, and so you see that it is the same, but the power of the 2 is bigger than this by 1. So it is equal to twice. Or it is twice 14, and it is equal to the last number of this of 29 of this sum. So we write that 21, or it is 2 multiply 14 plus 1. Oh, okay. So if we return here, we can say that if this is true, we say that A equal to R by modulo 3. And it is interesting that this equation is very similar to our usual equation, such that for example, if we know that B equal to R by modulo 3, so we can say that C is equal to this number by modulo 3. So, if we have the answer of the previous step, so we can find the new answer. In this case, we can say that we have three ability that R equal to 0, it is equal to 1, and it is equal to 2. So we write three states. That I equal to these three residues. And we know that initially we have 0, so the initial state, it is 0. And, for example, if we see that the first character is equal to 0, so we say that new residue equal to 2 multiplied by the previous answer, 0, plus 0. So the new answer is equal to 0, 2. So I can write it like the edge that starts with the vertex 0 and ends with it. And if it is equal to 1, so the new residue will be equal to 1. Okay, then if R equal to 1, and we know that B has the this number as the residue for this when we divide it by 3. So if we have new character equal to 0, then we say that the new residue will be equal to 2. If it is 0. But if we find new number equal to 1, then I say that the new residue will be equal to 1 plus 2, it is equal to 0. And then we can repeat this to this number. Because, for example, 2 twice 2, 2 multiplied by 2 plus 0, it is equal to 1. And if we multiply 2 by 2 and add the 1, so we got the 1. And it is DFA that can make the result that we need. For example, if we have, for example, number 129, we know that it is equal to this sum. So in the binary system, it is equal to this number. Yeah. So we start with the 0, then we see 1. So I here we will here we were at this state, then we see 1 and we go to this state. Then we see 0, we go to this state. Then we see 0, 2, and a lot of zeros. And then we see that we end with the I make a mistake. This equal to 2 in the 0, so need to erase 1. And then we see that the last number is 1, and we go from this state to 0. So I can say that this number will be equal to 0 by model 3. So we can implement this dfa in the realization, and then read one character and change our state, and the final state is equal to the answer of our question. So we can say that if we end this if state, then E answer. So it is the first application of the DFA, and the second that we talk about after break time will be Knuth Morris Pratt algorithm. And it is algorithm that try to find the substring of the given string that is equal to word that is to given initially. And we use dfa to make this algorithm work. So now we have break time, and if you have questions, ask me after break time. Okay, so в общем, сейчас можно. Okay, I open it and see what is the Correct bracket seconds. Okay. Yeah, I understand you. And really mean. The definition of the correct bracket sequence is very similar to this definition, because if you try to understand what is it, we can set we can define it by the induction. For example, one of the definition of correct bracket sequence, that if we have some brackets, we say that empty sequence, this sequence, this and this are correct. Then if we have a sequence S that is correct, then this sequence is too correct. And yeah, and if we have two correct bracket sequence, then we say that the concatenation is too correct. So all the strings that, all the sequences that we can get as the induction operation, such that add two brackets or concatenation, they are all correct, and no other lines are correct. So it's all, I think. Оставьте на том. Gotcha. Okay. So you can see that in the first example, there is only one pair of the brackets that is correct, because if you try to find 4 brackets in this sequence, we need to get all of them, but in the first pair, in the circle brackets, we have in it not the correct sequence. So the answer is equal to pair of two brackets in the first example. And in the next example, it is the similar, but it's more complicated. Так. В общем, сейчас. And now we have break time, I think, for 10 minutes, and then we start second part of the lecture. We have no students here. Wait for... Подождите пару минут. Сейчас надо узнать, что студенты так к лекциям относятся безобразно.
Вот появился.
Да, сейчас. Можете включить микрофон, там слышно?
Да.
Hello, and why your colleagues are not here in the offline or online? Do you know? Okay. So we continue with Knus with Knus-Morse-Pratt algorithm. And what is it? Firstly, we have some word x and we have string s. And the task is to find all the substrings in the S that are equal to x. What is interesting? Of course, we have native solution. With a space complexity O from n and time complexity m multiply n, we can compare all the substrings with the x. So we know that the number of substrings with the length of m is equal to n minus m, and asymptotically time that we spent on it is equal to multiplication of these two numbers. And of course, it is very bad that we have time complexity equal to multiplication of these two numbers, because m can be asymptotically equal to n, and we have here n square, and it is very bad. So of course we can use some dynamic solution, and to understand what is it, we can try to understand what is the comparison between the two strings interesting in it. Firstly, if we have, for example, if we have x equal to this line of the character and s equal to this line, then I want to say that for all for example, if we set s is index equals the prefix of this string, for example, this is s7, we can make additional task to find the maximal suffix of this string. That is equal to prefix of the string x. Okay. Additional task. As you remember, one lesson ago, we talk about different dynamic algorithms that connection with the two some additional tasks that we solve, and then we solve the common task, the general task, with the using the answers for additional tasks. So the additional task, find find the maximum prefix of the x, that is the suffix of s with index m. It is prefix the s with m characters. So, how to find it? And in this case, we use the DFA. That has states equal to prefixes of the x. For example, we have 0 prefix. We have prefix a, b, b, a, and a, b, b, a, b. And this is the states of the DFA. Of course, the initial state is equal to 0. And we can write these edges in the very understandable way that they are equal to these characters. And in this case, it is interesting that we need some additional edges that make from this DFA NFA, non-deterministic finite automaton. But it is very simple to understand how to find new the answer for the our task. So, firstly, if we try to find the answers for this additional task for this string, for the empty string, of course, we know the answer empty too. If we add one character a, so we see that it is equal to first character of x, and we go from this vertex to this vertex by this edge, and we repeat it to the S2 for this prefix of the S. And we repeat it for the third prefix, ABB. But then we see that the next character is not equal to A. And it is interesting to understand what we need to do. To understand it, we can find the maximum suffix of this word that is equal to some prefix of x, because if we cannot find a prefix of x equal to a and then 3 characters b, then it means that the maximum prefix of the x is less than this prefix. And it means that we can find the maximum prefix of x that is the suffix of this prefix. So I can say that the maximum prefix of x that is the suffix of this word is equal to 0, 2. And of course, if we have 0 suffix, then we can go by the HB here too. So the answer for additional task with the substring S4 is equal to 0, 2, because there is no suffix of this substring that is equal to one of the prefixes of x. But then I see that there is A, and I continue our algorithm and see that it is equal to S with index 5. Okay, and then I see that it is the S5. It is the maximum suffix of it that is the prefix of x. And then I see the character A. And I see that in this graph, we have no edge between this vertex and this with the character A. And I need to find such link or such edge that start with this vertex and end with it. So I see that the maximum suffix of this word, that is the prefix of the word x, is to A. So I make a loop here. So S with index 6 here too. Okay. Then I see that for S7 prefix of the S with the 7 characters, the maximum prefix is AB. And I see here that if we read this character, I go from this vertex here by this edge. Then I see B. I go here. I see A. Go here. And I see B. Go here. And if, for example, some prefixes is in the last vertex of the this finite automaton, it is equal that last characters of S of this prefix, the last characters is equal to X. And so we find the substring in S that is equal to X. So all of the prefixes that... Почему у него вообще отрубается?
30 минут максимальный интервал.
А.
Ну, я посмотрел на настройки. Больше.
Понятно. А почему вообще видеокамеры есть интервал? Сколько они могут в лайв-режиме снимать?
Ну, в лайв-режиме, оказывается, у него есть, других нет.
А, других нет? Понял. Okay. So I can say that the addition task, the answers, if we find the maximum prefixes of X, that is the suffix of the prefixes of the initial substring, initial string, then we say that number, for example, of the substrings in S is equal to number of prefixes that we find here. For example, now we see that the substring equal to all the string S is equal to is here. So we say that last 5 characters here is equal to X. So the substring of S equal to X is the last 5 characters. So if we have this finite automaton, we can find the answer for this additional task, and we can find the answer for the initial task. And we need to understand how to find these edges and find these links. Yeah, it names as suffix links. So I can repeat this Okay, firstly, we need to set these edges. And then you need to write here suffix links between these edges. And to suffix link connects the vertex V with the U. If U is the suffix of V, and it is the maximum suffix. For example, we see that for A is the suffix, the maximum suffix. So we can write here, but we find the suffix that is not equal to all this word. So I write here this suffix link. For this word, I cannot find the prefix of x that is the suffix of it. Here too. For this word, I see that I find the suffix a, and so I write here the suffix link between this word and this word. And here I find these two words, these two characters, a, b, that is the prefix of x, so I connected it with this vertex. And then we have some finite automaton with the edges with characters a, b, and the suffix links. In the common case, this links has empty character, and it is one of the model of NFA. Of course, it is non-deterministic finite automaton. So to construct it, we need to find all of the suffix links, and if we construct it, then by the online algorithm we can go through it, find all the states for all the prefixes of the substring, and then if we return to the task to find all the substrings. For example, if we need to find one of the substrings that is equal to x, we say that if first time when we go here, go to the last vertex, then we say that we find the substring in the S that is equal to x, and we return true, for example, that for the question. But if for all of the prefixes of S we stay on the previous vertices, then we say that we have no substrings that are equal to x. So after we draw or implement this NFA and go through it by this algorithm to solve this additional task, then we can find the answer for the initial algorithm. So time complexity of it. It is equal to, or from n plus m and space complexity all from m. And of course, space complexity is still better than the native algorithm because usually m is less than n. So it's about Knuth-Morris part algorithm. Okay, and can you ask some questions about it to understand better it, and then we go to the other algorithms. And talk about NFA. Guys, do you hear me, and do you have any questions?
No.
No. Do you understand this algorithm? Or you need, yes. Okay. So the next part, it is NFA. And now we talk about other types of finite automaton, and next time we talk about other algorithms that are connected with the finite automatas. So the third part, it is NFA. We know what is the DFA, and you remember that in the definition of DFA, it is the definition of DFA. I say that that it is deterministic if for all characters and for all vertices we can find 1 or 0 edge from this vertex with this character. Yeah, we cannot find a vertex such that that have two adjacent edges with the same character. So in the NFA, this non-deterministic finite automaton. We have now 5 restriction. And the other properties that I write here in this slide are equal for NFA. So it is the collection of vertices and edges such that for all the edges we set the character that is connected with it. And we have one distinct vertex that is the initial state and some vertices that we name as the final states of the automaton. So that's about definition. What is interesting for this non-deterministic and deterministic automaton? Of course, if we have automaton A, non-deterministic, we can say about language this automaton. As we say in the first part, that all the words that equal to path from initial state to the final state, all of these words will be in the automaton, or in the language of the automaton. So state is equal that if we have NFA, so language of this NFA will be regular too. So we can say that all the languages that we can define as the language of the NFA, some NFAs, they're all regulars. And there is other statement that if we have automaton A, we can find DFA B such that LA equal to LB. So it is interesting that if we have non-deterministic finite automaton, we can construct DFA with the same language in it. But it is complicated that it is very usual for the finite automatons that if we try to determinize some automaton that is not determinized initially, we find a graph with the exponential number of vertices. So if we have NFA here with n states, So sometimes we get graph with the two n states. So if we try to determine some finite automatons, we get exponential number of states. And it is bad, of course. So in different applications, you cannot use DFA. For example, if you remember regular statements, we can set L as the words for example like this. Yep. It is the words with the A in the 7th position from the end of the word. So it is simple to find n of A with this language, because we can set the initial state with two edges A and B. Let's set A here to this state, and then we say we draw 6 additional states and add these arrows here. Yeah, and then we say that it is the final state of this automaton. It is the vertices of this graph. Okay, and we can see that it is the NFA because for this vertex we have two different edges that start with this vertex with the same character. So it isn't deterministic. Finance automaton. But of course, language of this automaton equal to L, and it is very simple to prove it. But you see, what is the number of states of this finite automaton? It is a question for the viewers. What is the number of states here? Guys from the Zoom, do you hear me? Okay, and do you understand what is the states, or what are the states of the finite automaton? We talk about it in the first part. States of the automaton, it is the vertices of the graph. And so, what is the number of states in this automaton? Guys, can you answer for this question? What is the number of states of this automaton? It is very simple to understand. Oh no. Explain it again. Okay. We return to the first part of the lecture. What is the finite automaton? It is the states, that is the vertices of the graph, and edges that has a characters from the alphabet. So we name it as finite automaton, and we say that it is deterministic if we know that from one state we go to the other state by the edge, and we say that it is deterministic if this restriction is true. But now we have non-deterministic finite automaton. And what is the number of the states of this automaton? If the number of states is equal to number of vertices of this graph. 8. Yeah. Nice. We have only 8 states. And if you try to find the automaton with the same language but deterministic, I can say that the minimum of numbers of DFA with the same language will be with the nearly 2^7 states. And you can find the Myhill. You can find Myhill Nerode theorem that has as a consequence this statement. So it is necessary to understand that if we try to make from NFA DFA with the same language, we can get the exponential number of it, exponential number of states. And so in some applications we use NFA because it is more simple to implement. And the last point of the today's lecture, it's about non-regular languages. Okay, and guys, do you remember the word NP-complete languages? The expression NP-complete languages. Will you repeat? Okay. Do you remember expression NP-complete languages? Okay, forget it. About non-regular languages. For example, language. With these words. Will be not a regular language. And you cannot represent this language as the DFA or NFA because it is not regular, and regular languages is equal to languages that we can represent as DFA. And why it is non-regular? Because it is a sequence of pumping them. So your homework for the next lecture to understand what is the pumping lemma and understand how to prove that this language is not regular. And then we start with this statement next time, and then talk about other algorithms that connected with finite automatons. So that's all for today. Все, можете выключать.
Thank you.